Hello. Today I'll be discussing the Reynolds stress modeling problem, or the closure problem, as an inverse problem. My name is Christian Lagares Nieves, and I'm currently a PhD candidate at the University of Puerto Rico at Mayaguez. I'll first provide some motivation and introductory background information for today's presentation. Firstly, let's discuss compressibility and boundary layers. The boundary layer is a very thin layer of fluid that occurs around an object where viscous effects become relevant. You can picture an object moving through a fluid, and there's a very thin layer where the velocity of the flow becomes small or equal to the velocity of the surface, which from the perspective of the flow is zero. So in this very thin layer, a lot of very important effects occur. The nature of these regions can be either highly ordered or laminar, where you can see layers of flow in a very structured pattern, or chaotic, in which case we refer to the boundary layer as turbulent. Turbulent flows are typically characterized by a dominance of inertial forces over viscous forces, and usually we use the Reynolds number to assess this ratio. The Reynolds number is often assembled as a general form, which is the product of a characteristic length and a characteristic velocity divided by the kinematic viscosity of the fluid. When an object moves at the speed or faster than the speed of sound in a medium, you can see a buildup of molecules that occur. This is because the pressure waves that are formed can't propagate fast enough, and you can see this in the visualization of the figure that currently appears in the top right pane, where you see pressure waves moving at a given velocity, and this velocity is dependent on a lot of factors. But when an object is moving at or above this speed, we say that the object is moving at supersonic speeds. Now, the governing equations can be averaged in time, and again, I'm not going to move through all of the necessary procedures to do this in this presentation for time's sake, but I go into much more information or much more depth in the actual report for this work. But this is typically known as the Reynolds average Navier-Stokes equations. There's a density-weighted form known as the Favre average equations, which are the ones shown in this slide and equations immediately to the right. This introduces multiple assumptions, but it creates 9 new unknowns for which there are no additional equations as part of the fundamental equations that govern the problem. This is commonly known as a closure problem, which is the problem that we're tackling in this work. It is this infamous problem that usually opens a plethora of research avenues, since how this problem is tackled results in a different type of accuracy-cost trade-off. You can be very accurate at a high computational cost, or you can be more lax in your approach, but at a higher performance. Typically, new equations and assumptions are introduced and solved coupled to the original set of equations. In this work, rather than introducing new PDEs, we propose the introduction of an explicit nonlinear equation to map from baseline quantities to the new unknowns, and the introduction of physics-informed assumptions to simplify the problem from 9 unknowns to a set of 4 unknowns. Here, you can see a general approach of what we follow for a neural network, which will be our nonlinear mapping. The blue squares represent a high-level schematic of the model, which essentially takes the input vector alongside local coordinates, transforms them nonlinearly along a main data path, and then creates one data path for each one of the desired outputs for the tensor. And this enables a sort of a natural evolution for each one of these outputs, while still having some amount of weight sharing in the early portion of the neural network. So we have a first level of nonlinear mapping to a high dimensional space, and then we have independent mappings from this intermediate space to the desired outputs in the tensor. The neural network has approximately 400,000 parameters, which is relatively modest given today's standards, and for any given output you have 24 layers. So roughly 12 layers in the original or the first half, and then 12 layers per output on each one of the final paths. For this work, we use the Narwhal supercomputer for the Navy, and training the neural network in a reasonable amount of time requires an efficient computational resource, which I just mentioned will be Narwhal for this work. The dataset contained just under 15 million training samples and about 5 million testing and validation samples. We tested many hyperparameters, perhaps too many to discuss in this presentation, but we settled on a batch size of 1024. We tried smaller batch sizes, but the model didn't generalize as well, which was one of the surprising finds. Model trained for over 60 hours for the results that we show here on a Tesla V100 and achieved over 50 full passes over the entire training dataset. The training dataset was stored in an NVMe partition at Narwhal's PFS to improve throughput and latency. The optimizer chosen was the vanilla stochastic gradient descent with momentum and linear learning rate decay from 0.1 to 10 to the minus 4 after 100 epochs, and was updated after every batch. The momentum value was 0.9. Now I want to slow down in this slide because it highlights one of the key pillars of what we set out to do in this work. First of all being that including domain-specific knowledge could lead to improvements for the model. And one of these domain-specific or physics-informed pieces of knowledge was the inclusion of a sign inversion. So in each one of the outputs, we essentially normalize the output so as to allow the neural network to operate on larger values internally, and then we scale them down to the desired range. And this sort of allows a more fine-grained output by the neural network. With this particular output path, which is one of the off diagonals of the tensor, just known as the Reynolds shear stress, or U prime V prime for conciseness, the left figure here showcases the output before the inclusion of knowledge about the sign. This term here is usually negative in nature. Before including the sign, the neural network had to sort of guess the sign on its own and sort of had to learn that the term was always negative. By including that, immediately we saw a huge improvement in the quality of the output. There are still some oscillations that ought to be resolved, but essentially we see a huge improvement already in the model's output quality. We then move to the main sort of structure of the tensor, and here you can see all of the 4 outputs, with one of the outputs being repeated in the tensor, sort of arrange them in the same order that you can see in the tensor. The main diagonal's quality is stunning, to be honest, for a first attempt. There are some oscillations that need to be resolved in that off diagonal term for the U prime V prime, but for being a first attempt, the results are very much promising. I'm not going to go into further details on the global error for the work, but they can be found in the report for this project. Finally, some key takeaways. We've seen that training a DNN is possible for approximating the Reynolds stress tensor. Providing more independence to each data path yielded superior results, as did the inclusion of physics-informed linear modifications to the output, which was also a testament to how coupling both a machine learning approach with traditional physics can lead to huge improvements and huge advancements for the field. The model could generalize very much outside of the Reynolds number it was trained upon, and assuming data of reasonable quality is available, it can also generalize to Mach number outside of its training range. We did test this, but the data we used had some numerical issues. Results were not shown, but they do show promise. And again, I'm more than willing to answer any questions over email or in Moodle, but feel free to let me know if anything is not clear.